In this lesson, we will delve into Task 1.4 of Project 1, which focuses on gear machining accuracy and tool installation adjustment. This section primarily focuses on the various factors affecting gear machining accuracy and the key points of tool installation adjustment. We will learn about the relevant concepts and the evaluation criteria of gear machining accuracy, understand the methods and the importance of tool installation adjustment, and analyze the precision mechanical design concepts in classic machining methods, appreciating the foundational role of traditional techniques in modern manufacturing. Gears play a crucial role in mechanical transmission, and their machining accuracy directly affects the efficiency, smoothness, and noise performance of mechanical transmission. Gear machining accuracy is typically evaluated using three main criteria: pitch accuracy, profile accuracy, and lead accuracy. Together, these determine the dimensional shape and positional errors of the gear. Dimensional accuracy refers to the precision of dimensions such as tooth thickness and tooth width of a gear. For example, in the gears of an automobile transmission, if the dimensional accuracy of the tooth thickness does not meet the standard, it may result in excessive or insufficient meshing clearance between gears, thereby affecting the smoothness of power transmission. Dimensional accuracy is typically controlled by tolerances. The smaller the tolerance, the higher the dimensional accuracy. Profile accuracy reflects the degree of conformity between the actual tooth profile and the theoretical involute. If the profile error is too large, it can lead to increased vibration and noise during the transmission process. Evaluation criteria for shape accuracy include profile, deviation, and others. Positional accuracy refers to the installation position of the gear on the shaft and the relative positional accuracy between the teeth. For instance, lead deviation falls under the category of positional accuracy. Excessive lead deviation can cause uneven force distribution during gear meshing, accelerating gear wear. Machine tool accuracy. The machine tool is the fundamental equipment for gear machining, and its accuracy directly affects the machining accuracy of gears. The rotational accuracy of the machine tool's spindle and the precision of its guideways, among other factors, can impact gear machining. For example, the radial runout of the spindle can cause profile errors and lead errors in the machined gear. The rotational accuracy of the spindle can be measured by two indicators: radial runout and axial movement. The accuracy of the tool plays a crucial role in gear machining accuracy. Errors in the tool's tooth profile and the quality of its sharpening will be reflected in the machined gear. Taking a gear milling cutter as an example, if the tooth profile of the milling cutter is inaccurate, the gear's tooth profile will also have deviations. The manufacturing accuracy of the tool is typically ensured by the tool manufacturer, but during use tool wear can also affect its accuracy. Therefore, it is necessary to regularly sharpen and replace the tool. The properties of the workpiece material and the heat treatment process can also affect gear machining accuracy. Different materials have varying cutting properties. For instance, materials with higher hardness may cause increased tool wear during machining, thereby affecting machining accuracy. Improper heat treatment processes can lead to gear deformation, reducing gear accuracy. For example, uneven cooling during the quenching process may induce internal stresses in the gear, resulting in deformation. Whether the tool is installed and adjusted correctly is directly related to the machining accuracy of the gear. If the tool installation position is inaccurate, it can cause various errors in the machined gear. For example, axial position deviation of the tool can lead to lead errors in the gear, while radial position deviation can affect the dimensional accuracy of the gear's tooth thickness. Axial adjustment. Axial adjustment primarily ensures the accurate axial positioning of the tool. In gear shaping, the axial position of the gear shaper cutter needs to be precisely adjusted to ensure the lead accuracy of the gear. Typically, dial indicators and other measuring tools can be used for axial position adjustment. During adjustment, bring the dial indicator's probe into contact with the axial positioning surface of the tool. Adjust the axial position of the tool so that the dial indicator's reading falls within the specified tolerance range. Radial adjustment is to ensure the accurate radial positioning of the tool, thereby controlling the dimensional accuracy of the gear's tooth thickness. In gear hobbing, the radial position adjustment of the hob is crucial. Radial adjustment involves setting the center distance from the hob axis to the worktable axis to equal the theoretical installation distance. A equals D2 plus D workpiece divided by 2. This is usually accomplished using a standard mandrel or a tool setting gauge. The radial feed amount during machining is then distributed by the CNC system based on the cutting allowance. The generating method is a commonly used technique in gear machining, with gear shaping and hobbing both based on the principles of this method. The core idea of the generating method is to use the meshing motion between the tool and the workpiece to machine the gear's tooth profile. In gear shaping, the gear shaper cutter acts like a gear meshing with the workpiece gear. Through the cutter's reciprocating up and down motion and the workpiece rotational motion, the gear's tooth profile is gradually cut. This classic machining method embodies precise mechanical design concepts. The application of the generating method principle allows for high precision tooth profile machining and enables the production of gears with various modules and numbers of teeth. It reflects the wisdom of traditional craftsmanship and serves as a cornerstone of modern manufacturing. For example, in the manufacturing of gears for aircraft engines, high-precision gears produced using the generating method can ensure the efficient and stable operation of the engine. Taking gear machining in automobile engines as an example. The precision requirements for gears in automobile engines are extremely high because the accuracy of the gears directly affects the power transmission and noise levels of the engine. During the machining process, it is essential to first select high-precision machine tools and cutters, ensuring the rotational accuracy of the machine tool's spindle and the tooth profile accuracy of the cutter. Then, through precise tool installation and adjustment, the dimensional and positional accuracy of the gears is guaranteed. In terms of tool installation and adjustment for gear hobbing, it is crucial to precisely adjust the axial and radial positions of the hob. By using high-precision measuring tools, such as laser interferometers, the position of the hob is measured and adjusted to keep the position error within a minimal range. Additionally, during the machining process, strict quality control of the workpiece material and appropriate heat treatment processes are necessary to ensure the performance and accuracy of the gears. The generating method principle and other precise mechanical design concepts embedded in classic machining methods such as gear shaping and hobbing are the crystallization of the wisdom of our predecessors. These traditional techniques continue to play a significant role in modern manufacturing and form the foundation for the development of modern manufacturing technology. As the new generation of mechanical learners, we must deeply understand and carry forward the essence of these mechanical sciences, while also innovating on the basis of traditional techniques. For example, with the development of CNC technology, we can apply CNC systems to gear machining, machines to achieve more precise tool installation adjustments and process control, thereby improving the accuracy and efficiency of gear machining. In this lesson, we primarily studied the aspects of gear machining accuracy and tool installation adjustments. We first explored the concept of gear machining accuracy, which includes dimensional accuracy, shape accuracy, and positional accuracy, as well as the factors affecting gear machining accuracy, such as machine tool precision, and workpiece material. We then focused on the importance and methods of tool installation adjustments, including axial and radial adjustments. We also analyzed the precise mechanical design concepts, such as the generating method principle, embedded in classic machining methods like gear, shaping, and hobbing. Through the case study of gear machining in automobile engines, we deepened our understanding of the knowledge learned. Finally, we emphasized the wisdom of craftsmanship in both inheritance and innovation. I hope everyone can deeply understand the foundational role of traditional techniques in modern manufacturing and continuously carry them forward and innovate in both learning and practice.